I don't know. All right, I guess we can get started. So the paper I'm covering is Loss Landscapes and Optimization in Over-Parameterized Nonlinear Systems in Neural Networks. So this is a paper by the following authors. They're Xiaoxu Liu, Mikhail or Misha Belkin, and Livin Su. All of these are researchers out of University of California, San Diego. And Xiaoxu Liu, I wish I had a picture, but I don't. He's a postdoc. I think he completed his PhD at Ohio State University. Belkin, he is a professor, and he is, I'll talk a little bit more about him in a minute. And Livin Su, he's a PhD student, and right now he is also working for Meta as a research scientist. So Misha has been working on optimization and data representation for machine learning for a long time. Recently, his interests include working towards a grand unified optimization theory of neural networks, if you could say it like that. So his lab has been working on all sorts of papers trying to understand loss landscapes, which I'll cover in a minute. So this is more or less an overview of this presentation. We're going to first introduce some context, a summary of ideas, and the notation. So we're going to talk about the notion of convexity, just as a refresher for all of you, because it's at the heart of this paper. Neural network loss landscapes, what are they, what they look like, and why they're so difficult to understand. Some main ideas about the paper, and a very, very dense notation and remarks page. And after that, it's all math. We're just going to look at the main results of this paper. We're going to look at how the results are motivated and what the implications are, and we're going to go through a lot of proofs in detail. Hopefully I made them understandable and I can explain them in a way that's easy to follow. So let's start. So I'm sure you all know convexity by now. If you've taken calculus, recall that we use a convex function in an interval. We can intuitively think of it like within the interval AB, any line that we trace from any points in this function will fall above the function values. We can readily extend this notion to multiple dimensions, just generalizing the idea of a line for that of a hyperplane. For differentiable functions specifically, convexity can be tested using the second derivative or the Hessian in case you have multiple variables. So that would be positivity of a second derivative in the scalar case, and in case the Hessian is matrix, we would need positive semi-definiteness. And then there's also the notion of strict convexity, which would be strictly greater than 0 and positive definite, but we're not going to deal with strict convexity in this paper. So why do we care about convexity? Well, first let's talk about neural network loss landscapes. So if we have a loss function, let's call it fancy L, that maps parameters from some parameter space to a scalar value. Actually, this should be typically non-negative values. If we have this map, then this sort of induces a sort of surface in parameter space.
So L is like a scalarization function.
Yeah, I mean, it's any loss function, any kind of neural network training objective. Generally, most of them are non-negative. And if they're not, we can probably scale them because they're bounded below. So this is a picture of what a neural, the loss landscape of a large neural network would look like if we could visualize it. As we all know, neural networks have millions, in some cases billions, and eventually trillions of parameters. So there's no ready way to visualize this. And also, this hyperdimensionality means that their study is very difficult. In hyperdimensional space, high dimensional space, some of our intuitions hold, some of them break, and it's just generally very hard to understand what's going on. Luckily, we've been able to rely on something called convexity analysis, something called optimization theory that we've inherited from previous years of optimization applied to not just to neural networks, but to machine learning models, and before that, just to function optimization more broadly speaking. So neural networks have benefited from a lot of results in optimization theory, but a lot of those results that we've inherited sort of rely on this notion of local convexity, that meaning convexity within local neighborhoods. So for example, here we would have a sort of local convexity, right? Because we can see that this seems to be a local minima. So a lot of our training algorithms, mostly their analytical properties are proved or are dependent on some notions of convexity. Now in practice, neural networks work really well, even if we throw away a lot of the super detailed analytical theory. We've been using gradient descent for a while and its variance. It all seems to work well, but we're interested in arriving at a more mature optimization theory for deep learning. So this is where this paper comes in. This paper makes a very controversial assertion. It claims that over-parameterized neural networks, meaning very large neural networks, feature essential non-convexity. This means that their loss landscapes are convex almost nowhere. This would seemingly mean that we would have to discard or reframe much of our understanding of neural network optimization, and this is part of the role of this paper as one of those beginning steps. So here, for example, we have a comparison of an under-parameterized model, and in these types of models, you will find typically a lot of spurious local minima, and you will have a lot of locally convex neighborhoods. By contrast, again, this is a low-dimensional visualization because we can only work in analogy, but if this were, let's say, a high-dimensional parameter space, loss parameter space, then we would see, as per the results of this paper, that actually the loss landscape does not feature spurious local minima, and that actually there's a connected set of global minima that has a positive dimension curvature forms a manifold. So before we jump into all the beautiful math, there's some notation, just so we're all on the same page. We're going to use bold-faced letters for vectors. We're going to use capital letters for matrices. Now we're going to use bold capital letters for either tuple of matrices or higher order tensors. So there's going to be a few tensors here, but as usual, we're going to try not to work with them. So very quickly, we're going to decompose them, typically along some dimension. We're going to use this shorthand for this set. We're going to denote sigma for activation functions, and also we're going to use the prime for the derivatives. Now this is an important one that I'll touch on in a little bit. Fancy F is the map from parameter space to network outputs. I'm going to expand on this in a minute. Fancy DF, this will be the differential map of Fancy F, and you can think of it like a Jacobian. Now we're going to have not bold-faced H sub Fi. This will be the Hessian of the map of S, the ith component of this map F. And then we're going to do the bold-face for the entire Hessian, which will be a higher order tensor.
Mario, one moment, but if it goes from into scalar, right? Like, how can we have indices in it if it's a scalar? If there
No. So, like, the neural network will be a scalar function. Well, not the neural network. Actually, yes, the neural network and the loss will be both scalar functions, but this is something else that I'll define in a minute. So you'll see what I mean. Because essentially, you can think of this as the collection of neural network outputs on the entire data set. So Rn, n is induced by the number of samples that we'll have, and we'll have a scalar output of the neural network for each sample.
See, that's confusing, because there are neural networks that have multiple outputs.
Yes, and they don't actually deal with that in this paper at all. They note that it can be done, that this analysis holds, but they only cover scalar functions.
So it's the output of the ith parameter into a scalar, like ith component of the output into a scalar.
No. It's the neural network output for the ith sample. Yes.
Yeah.
So it will be.
Sample.
Mm-hmm. So this would be the gradient of the neural network evaluated at the ith sample with respect to the parameters. That Hessian.
I see. So then the differential is you fix the sample is fixed.
Yep.
But you change the weights inside the neural network.
Yeah, that's exactly right. And then lastly, we'll use this at some point. This is a set of of weights that the neural network undergoes through gradient descent, so we call it the optimization path. And this one is going to be useful since the Hessian is a higher order tensor in this context. We're going to define this norm on the Hessian, which is basically just the regular 2 norm on the largest of the 2 norms of all the components indexed on the sample. So like we have here is the n. This will be indexing the samples. So we're just going to grab the largest Hessian of a given sample. A few assumptions that we're going to make for this analysis. Yep.
That's at a particular value of the weights.
Yes, yes.
So which sample gives you the largest tension may change.
Yeah, yeah, exactly. So some assumptions, I always have trouble saying this, so I don't want to say a bad word, but Lipschitz continuity. So we're going to assume that these maps are going to be Lipschitz continuous, which essentially bounds the rate of growth, or the growth of this function, right? And then if this map is this way, this is a result that we're going to use at some point. You don't know what k is yet. I'm going to go over that in a minute. We're also going to assume that this map is smooth, and also implicit is the continuity of the Hessian. Now we're going to go over the supervised learning setting, and as we can see here, in a typical supervised learning task, we're given training data, where we have some input vectors for our network, and then some scalars could be labels, or it could be values in the regression case. And essentially the task of the neural network is fitting data. You can think of it that if we're perfectly fitting the data, we would be sort of interpolating the data. So mathematically, this would be exactly or approximately solving a system of n equations, where we would have one equation for each sample, right? We have this system, and we wanted to fit all of these samples, and each of those samples induces an equation that we need to solve, and we need to solve that system jointly, right? All those equations jointly. So we can aggregate all of that in a single map, and this is where this fancy F comes from, where now it's almost like the data points, the input vectors are baked into this map. So this map is only concerned now with the parameters. So now typically we solve it by minimizing some loss. Most of this paper is concerned with the typical square loss. And last note, again, we are interested in over-parameterized systems. This is going to be an implicit assumption that we need to remember throughout this paper. M is going to be larger than n. This is going to show up in some proofs. Yep.
Which is larger?
N. Yeah, so
the number of parameters is larger than the training set.
Yep.
And the capital N in that, is that supposed to be a small n?
Where? Oh, this?
Yeah.
Yeah, that's supposed to be a small n. Okay. So yeah.
One question. Can we also say that, for example, not a very large data set, but for example, a data set of 3 with 5 parameters is also the case for this? Or it only works with a large number?
Well, it actually, so this is something that's a little bit hand-wavy, because it's not as simple as just comparing these numbers, even though the paper kind of reduces to this. They note near the conclusion and in some other aspects, and also in some talks that Belkin gives, that it's a little bit more complicated than that, because you can think of the data points, especially for large networks, it's not necessarily the implicit constraints that the data induces on the system is not just as simple as number. You could have data that induces constraints that are comparably more similar to the number of parameters, even if the actual number of data points is very small.
I see. So,
yeah.
So it's not only course of dimensionality.
Mm-hmm. Because note that we don't touch the dimensionality of the input at all, and that is kind of something that is ignored in this entire analysis. So a key construct throughout this paper is the tangent kernel. The authors borrow inspiration from a paper on neural tangent kernels, which is analyzing this construct for infinite width networks in the limit. Of course, we don't deal with infinite width infinite width networks, and we don't even try to get to that limit, but we are dealing with very large systems, and this is useful for proofs, and it's also useful for intuition that mostly I'll be skipping because there's just so much content, but there are some nice observations that the authors make about the constancy of this thing for larger and larger systems. Another thing that's useful that we're going to use later is that we can describe the gradient of the loss as the transpose of this differential map times this difference. So in that case, when we try to get the square normal gradient, we can get it like this, and we'll see where we'll use it in a minute. I guess some intuition that you can think about it is that if you think of the ijth component of this tangent kernel thing, it will essentially be doing a sort of vector similarity measure between the gradient of the ith sample with the gradient of the jth sample. So it sort of does a sort of alignment of gradients measure. Like a cosine similarity, the cosine similarity is related to the dot product of vectors, so you can think of it as a sort of a vector alignment in that sense. So now we're going to talk about essential non-convexity, and this is one of the main parts of the paper. So we're going to do a little bit of a proof overview, go through the nasty details, and then I'll talk about some implications. So one of the main propositions in this paper is proposition 2, and it says local non-convexity. Let the loss at W star equals 0, meaning that W star is the global minimizer of the loss. Furthermore, assume that the differential map is non-zero, and that the rank of the Hessian of the ith component of the map F at W star has a rank greater than 2n for at least one I in the set of 1 for n. Then this thing is not convex in any neighborhood of W star. So we're going to see this one. We're going to see another one that has more to do with the non-existence of local minima. There's a lot of slides, there's a lot of stuff here, so I hope I have time for everything. So we start with just the Hessian matrix of a general loss function takes on this form. This is just definition. And now, again, recall, this notation is kind of annoying, by the way, because we need to pay a lot of attention every time we have an H to the sub-index, whether it's talking about the Hessian of a map or the Hessian of the loss. So that's an important distinction to keep in mind throughout these proofs. So we will consider the Hessian matrices of this loss around a global minimizer, and we're going to perturb it by some delta vector. So we're going to perturb it in one direction, and then we're going to perturb it in another direction by this delta. And it's going to be in a sufficiently small neighborhood of the minimizer. It's going to be a really, really small neighborhood. Then the Hessian loss of these points become this. Notice that it looks super nasty, but all we're doing is we're grabbing these forms and we're plugging it in every time we see W. For simplicity's sake, we're going to grab this entire thing and we're going to call it A of W star plus delta and A of W star minus delta. And these, note that if you look at the shape of these things, this is going to be an n by m matrix. This is going to be an m by n. This is going to be m by m. So this entire thing is going to be m by m. But because the rank of the differential map is n, is at most n. Because it's because of the shape of this. Because n is smaller than m. Remember, it's implicit every time. Then the shape of this, the rank of this is going to be at most n. So I'm going to scroll up a little bit. So now by the assumption, and remember this assumption is just that the rank is greater than 2n, at least one of the components of this Hessian will be there's a component, by the assumption there's at least one component of this Hessian that will have a rank greater than 2n. Now, by the continuity of the Hessian, we have that if the magnitude of this perturbation is sufficiently small, then the ranks of these things will also be greater than n. Meaning, if the Hessian at this point is rank 2n, greater than rank 2n, then if we move just a little bit, because the Hessian is continuous, then we're still going to be we're still going to obtain a Hessian that has rank greater than 2n. Now, because of all this, we can find a unit length vector v such that that falls in the null space of this thing. And you can think about it like this. So the rank of this thing, of this A matrix, is at most n, but the matrix is m by m. So there's going to be a non-trivial null space there, which means that we can do that. We can find this B that is not zero, non-trivial element of the null space. Now, since the rank of this H sub f is greater than 2n for some k, we know it's greater than 2n. That means that in this thing we can also make sure that the vector does not zero out this guy, this H sub f. So because of this difference in null spaces and in dimensionalities, it guarantees that we can find a vector that will be in the null space of A, but will not be in the null space of this H. And now, consequently, if we grab all of these quadratic forms for each of these components and we put them in a vector, then that vector will definitely be non-zero because the kth component will be non-zero. Now with the same vector, if we grab the same vector, all we're doing here is we're multiplying it on both sides of the thing that we saw earlier. And notice that by the construction of this vector, remember it zeroes out with A because it's in the null space of A, so this entire term will disappear, which means we'll be left with this. And of course here's where the end out after you distribute them throughout, and then you'll have some depreciable terms. So this is where it starts getting a little bit tricky. We want to show that for a sufficiently small perturbation, when we look at these two quadratic forms, they cannot be non-negative simultaneously, which would immediately imply that this Hessian of the loss is not positive semi-definite, which should mean that it is that we don't have convexity. So with this condition, we look at the first case, and the first case is where one of these things is negative, in which case that's it, we're done, right? Because we would have that one of these is non-negative, and we're trying to show that they can be non-negative simultaneously. And if this thing, now this one's a little bit tricky. If this makes your head hurt, I get it, but like we can ignore most of what's in here. So otherwise, if this thing is greater than 0, then by the continuity of the Hessian, we can find, we can do this decomposition here. So basically, it's like we keep the positive thing, and if we were to add these up, we would get the original thing. So we do this decomposition, and if you look at this term here, this is the key term. Because of the continuity of the Hessian, we can pick a delta that is arbitrarily small, and certainly that it is small enough to make this different depreciable, because these two things would be evaluated at sufficiently close points. And then that would be basically as close to 0 as we want, which means that we can wrap it out in this nice big old term. And then, because this thing is positive, and the construction of this thing has the negative in front, then it will be negative. Yeah, it's tricky, this stuff. So in conclusion, if we have a certain delta which is arbitrarily small, either of these guys will be small, which means that the loss will have no convex neighborhood around this global minimizer W star. So implications. The non-zero curvature of this curve of global minimizers, you can see kind of at the bottom of the valley, it's the same picture. What does this imply in terms of convexity? It implies that convexity is actually not the right framework for analysis for these over-parameterized systems, not even at the local level. And it's kind of a big deal. So we need a replacement, right? Like we can't just like throw it away. Do we need to throw it away? I mean, seemingly our neural network string is fine. We keep doing more and more magic with them.
After you finish, I would like to return to mathematical derivation.
Yeah, okay. So, neural networks are PL star. What is PL star? We'll see in a minute. We're going to define what PL star is. We're going to motivate it a little bit. We're gonna give some arguments and some proof for the components and also some results. So this is the, and I don't know if I'm saying this right, but it's the Polyak-Loja-Seewicz condition. Okay, well, granted we have someone who can pronounce it here. I'm gonna call it PL for short because I can't pronounce it. So we say that a non-negative function L satisfies the mu PL star condition on a subset of Rm for some positive mu if the norms, the square norm of the gradient of L is bigger than a mu times the loss at W for every W in the set, for everything in the subset. So the hope, or the cope, is trying to use this to reframe optimization in an essentially non-convex world. This has been used, it's a theoretical framework that's been used for optimization before. It's been used for optimization in physics, and there are some nice results that can be explored if we can show that our large neural networks fit in the framework.
So it's already shown success in physics.
Some, yeah. I mean, you can find some, but I didn't do too much of a deep search on the successes that it's had. I guess another remark is that technically this condition would need this term on the right-hand side, but since we're concerned with losses that have evaluated this minimum of 0, then we can ignore it. So we're going to look at some argument dependencies. I'm not going to prove everything because it would take too long, but I'm going to prove the main results definitely, and if there's time, then I'll go back and I'll prove some other things. So we have this definition of uniform conditioning, and this basically says that we have a map, that our map is mu uniformly conditioned for a positive mu on the subset S if the smallest eigenvalue of its tangent kernel, and here's this construct again, is greater than mu for every W in S. And then we have theorem 1, which is one of the workhorses in here, which says that if we do have uniform conditioning, then we get that thing satisfies the PL star condition. So if fancy f of W is mu uniformly conditioned on a set S, then the square loss function specifically satisfies the mu PL star condition on S. And the proof is actually not that difficult. Here we use that remark that I made earlier about the neural tangent kernel, where we can use it to expand like this. Now, because the map is mu uniformly conditioned, we have this property, so we can just plug it in here. We know that this quadratic form will have this lower bound here. Will be greater than this. So this one is just not too difficult to prove. It's just 1 line.
And what is mu? What is mu?
It's a number that it depends on your tangent kernel. Meaning it would be like a lower bound for the smallest eigenvalue of your tangent kernel at W. Well, all W in a neighborhood.
So the tangent kernel has, I mean, the rank it's m by m, but has rank n.
No, it has rank m, but it's m by m.
It's n by m.
Let me go back. All the things get really confusing with the shapes.
Yeah. You had a picture with the shapes.
Yeah, this would be because this is m by n, right? So let's see. Okay, it's n by n. The tangent kernel is n by n. N by n. N by n. Sorry.
And Mary by Mary or Nancy?
Nancy by Nancy. Yeah.
Okay.
So wait, hold on. Let me look at the transpose again. This gets really confusing.
Sometimes it's nice to look at the picture that you have.
Yeah. Okay, now I got lost in my slides. Oh, there we go. Yeah, so it'll be n by n because it's n by m, and then this would be n by n. Okay, so now we can use that uniform conditioning idea to have this thing called Hessian control. And the idea of the analysis is that we can bound the change of the tangent kernel of the map in terms of the norm of the Hessian of the map. And if we have that, we would like to prove that actually that means that we have PO star conditions. So there's a theorem 2, which says that given a point W0 in parameter space, suppose that the tangent kernel of the map at that point is strictly positive definite, meaning that its smallest eigenvalue is greater than 0. If the Hessian spectral norm bounded in this way, so like this would be like the largest component is bounded by this ugly ratio. If this holds within this R ball around W0 for some positive mu, then the tangent kernel KW is mu uniformly conditioned on the ball, hence the square loss satisfies the UPL condition because we're bounding. So we're bounding that gradient. So first, let's consider the difference between the tangent kernel matrices at W and at W0, sub-0. So let's scroll up. So by the assumption, we have that for all the vectors in this ball, this thing, the Hessian of those vectors is bounded. The norm of the Hessian of those vectors is bounded. And again, this is our fancy norm, which would be the greatest component. We pick the greatest component. So for each I in the set, we would have this, just construction of this, just a reminder of what this means, the notation. So now if we consider an arbitrary point W in that ball, for all the I, we would have, for all the components, we would have that at the ith component we have the differential map evaluated at W0 plus this integral here. And here we're essentially going through the line integrated through the line segment between W0 and W. It's like a sort of interpolation inside this ball. So from that they can conclude they put a bound on this difference, and this is actually kind of an unintuitive step, and there's a lot of these in here. So what they're doing here is they're grabbing this, they're subtracting it from both sides, so we get this on the left, and then they're putting a bound on this. And what is this bound? Well, you can think of it like, and I drew a picture because I work with pictures. You can think of it like, well, this is integrating a bunch of values in an interval, right? So if we actually just grab like the largest of those values, so we get the superior one, supremum here, of the in those values in that integral, and then we just like we just project it across the interval, we're going to get something that is strictly greater than the integral we're working with. So that's, I think, where that bound comes from. And then once we get this form, we can use this very convenient identity that we have here, and we also know that this will necessarily be smaller than the radius because all of this is inside because this is center of the ball, and this is inside the ball. So this norm will definitely be smaller than R, so we can bound it in this manner, and then we can just cancel the R's. So I think it's pretty clever. I think it's cute. So in the second inequality, we use, again, this thing, which was just mentioned here, where my thing is covering it. Right here. So in the second inequality row, we use that fact, we scroll up. And from that, we can just put it all together and get this bound for this difference. And we scroll up a little bit more. So now we use that to prove the norm of the spectral bound. All of that was just to the spectral what? What? You said sorry, to put the bound of the spectral norm of the tangent kernel. Sorry, I get mixed up my words. So now we look at the thing that we actually care about, which is this difference. And we do some linear algebra here, which this is not, I mean, here we just like expand the definition of the kernel, and then we expand this, and then we bound it in this manner. And now these are like the non-intuitive steps, I guess, where for here they just use the fact that the true norm is greater, less than or equal to the Frobenius norm. So we change these for Frobenius norms. Here we make this replacement because this is just an assumption. Oh, sorry, this is from Lipschitz continuity as well. And we use these two to essentially convert this entire expression, this entire upper bound, into just lambda 0 minus mu.
Okay. The F norm involves all of the eigenvalues, not just these.
I think, right, because we get this one from over here. That's what you mean. This is up, we derive it here. This one. So then we use the triangle inequality, and we see that the smallest eigenvalue of the tangent kernel is greater than mu, and then finally we can say that it is mu uniformly conditioned in the ball by definition 3, which is exactly that we can put a lower bound of mu for every w in a subset S. That's why we started around this analysis around this ball, the subset. And then I guess before we can prove that neural networks are PL star, we need, I guess, one last requisite, which is just showing that certain compositions do not change the condition. Namely, these would be the nonlinearities. So I'm going to introduce theorem 3 here. I'm not going to prove it. I don't think. No. I guess I can prove it, but I'm kind of running low on time. I have so much to cover. So if a system F is mu uniformly conditioned in the ball, then we can apply a transformation that will essentially keep that. I kind of need to speed up a little bit here. Okay, so now we look at the actual neural networks, and we're just going to assume that theorem 3 is 3. We're not going to prove it. And we can define it in this manner. Just we're going to have our hidden vectors here, where we apply some nonlinearity, some matrix here, and some previous output matrix multiplication here. So if we define them in this manner, it's essentially a dense network, although the bias is not explicitly included here, as we all should have learned from Intro to Machine Learning with Dr. Boley. You can kind of make that implicit in the data set. The authors only consider sigmoid activation functions and not ReLU, which is kind of a big limitation here. But they do show that it would work for conditional and residual networks in the appendix. Okay, so why does this satisfy this is the main result, I guess, that showing that it does satisfy the PL star condition. So consider this neural network. So again, this is not fancy F. In a random parameter setting where we have like an initialization that is just normally distributed for all the layers. And now we suppose that the last layer activation is that its derivative is bounded by some, I'm going to call it B. And that lambda sub 0 is set to the smallest eigenvalue of the tangent kernel at the initialization, which will be greater than 0. And also for any mu in this set, the width of the network is given like this. So this is like, I guess you could say it's like big omega on steroids. It just means that we also ignore values are polynomial and the logarithm of the
and what is R?
What?
What is R?
The radius of the ball. I guess I didn't say it here. I didn't stop. Mu PL star condition holds for the square function, square loss function in this ball of radius r. So we split into two parts. We first kind of show it without thinking about the activation, and then with the activation. It's gonna actually come pretty quickly because we can just use the theorem for the composition for the activation part. So if we just look at the linear activation, in this case we would just have that the linear activation is just like the identity map, and in this case we can see that p equals 1 satisfies it, because if you take the derivative of this with respect to itself, it's just, you know, if you take the derivative of c with respect to c, you just get 1. So it will, so the output of the network has a linear form. Okay, and then we can consider this transition to linearity just with high probability over the initialization. The Hessian spectral norm satisfies this, and from this we can plug this in with the condition for theorem 2, because using this theorem 5, which they actually I believe they inherit from a different paper that works on this. They can put a bound on this thing, and then we can use the PL star condition via Hessian norm now, and then that would kind of conclude the proof. So for step 2, we're going to look at the cases where we have a nonlinear activation function, and really this is just an application of theorem 3. We just defined this transformation map that fits the criteria for theorem 3, and then we get the result. And there's some other stuff that they talk about in here, but I'm going to skip that. So implications and other remarks. For sufficiently large neural networks, we have this satisfaction of the mu PL star condition, and this kind of unlocks this new analytical framework for us to study neural network optimization and address this maybe like loss of tool or insights or techniques that depend on local convexity. The good news is that, you know, like if there's results about stochastic gradient descent that depend on local convexity, well, we can actually show that PL star is sufficient to get those same results of exponential convergence and so on. So there's some argument dependencies here. Actually, I don't think that they're relevant, and I kind of need to speed through some of this. So I don't know if I can go through the proofs in depth. So the PL star condition implies existence and convergence. So this is kind of the main result, and they prove it by induction. I'm going to kind of sketch the proof this time. So, and the nice thing about this proof is that they don't do it for just the loss. This is general for any loss, which in turn makes it work for all the analysis we saw previously, which consider only the square loss. So existence of a solution are the two things we're going to prove, and then the conversion of gradient descent with a given step size, it will converge to a global solution with an exponential or linear convergence rate. And here it's this argument dependency on the condition number, which on the previous slide. So starting with this, they prove it by induction. The base case is actually trivial. We don't need to look too carefully. The induction hypothesis is that for all t greater than 0, Wt is within the ball with this radius, and this is the k rate. So if we put it to the power 0, then this just becomes 1. This is greater than or equal to this. So in the case basis is trivial. And this one, I guess, I don't think I can cover because I want to get to a more interesting result, I think. At least to me it's more interesting. So anyway, they do just typical induction proof. You do the base step, you do the induction step, and then you conclude that the hypothesis is true. So this one, 8. Okay, so this is another interesting theorem that just follows from the application of theorem 4 and 6. So Okay, so I want to talk about this because I think there's two results that I think are really interested. One of them is the path connectedness of global minima. This is like one of the most interesting results to me, which we saw in this, what we saw in this picture earlier. One of the consequences of this analysis is that actually the set of global minima is connected. And as we mentioned, they also talk about the fact that there would be no spurious local minima in these large over-parameterized systems. For that, they actually borrow a previous result from a paper that came out shortly before this. But the path connected one is also related to this local minima one. So I'm going to cover kind of both in one shot. So no isolated local minima. So consider this feed-forward network of the form we saw earlier, basically. So if it has this specific width, given a local global minimum W star of the loss function, there will always be other global minima in any neighborhood of W star. I mean, that's kind of impressive, right? Because it means that if you find a global minima, then as long as you have a network that is this wide, then you will always find other global minima around it in any neighborhood. At least one. So for this, to prove this proposition 6, they talk about path constancy. So this is actually a result that well, this is a definition and they will borrow a result from another paper. So this idea of path constancy just means that if you fix the loss, there will be a constant path of parameters that will join a path of constant loss parameters that will join any two given parameters that can be joined. So it's basically like you can find a path between two guys. And let me give you an example here. So if you have this guy here, and let's suppose that the contour of like the same loss value is like this, it just means that you can find a path between these guys. You can find all these different parameters with equal loss value.
Yeah, but this picture contradicts it because you can have the height of a ridge on the left side and the ridge on the right side, and you're not connected.
Right. Yeah. Well, maybe it contradicts it in this two-dimensional picture, right? Well, in this three-dimensional loss landscape, right? I don't know whether that would. But there's a bunch of criticisms that I have for this paper too.
Right.
So, now, how they prove this? They prove this using this kind of esoteric construct, which are called block parameters. So basically, are parameters that are kind of satisfying these things, where the first one needs to be like this, where it's kind of like sparse after a given point, or just zeroed out after a given point. And for these layers in between, they need to look like this. And for the last layer, it needs to look like this. And we will call this an S upper block parameter. And then we have this definition for the lower block parameters, which is just kind of flipping this idea. And there are path connections to block parameters. This is, I guess, the workhorse of this for this proof of the proposition 6. In this, they borrow it from this paper, No Spurious Local Minima on the Optimization Landscapes of Wide and Deep Neural Networks. So this proposition says that for every parameter W, and then you have this S number of training samples, then S here is, again, will be the S that we use to kind of determine this cutoff point in these block parameters. There are upper block and lower block parameters that connect your parameter. So if I give you a parameter, and if I give you a parameter, you can find an upper block and a lower block parameter that are path connected to my original parameter. That's kind of the idea here. And this is, again, a proposition that they borrowed from previous work. And then they prove proposition 6 by saying, okay, well, using that tool, let's suppose that W star is an arbitrary local global minimum of the loss. So according to proposition 7, there exist upper block parameters, upper block and lower block parameters such that we can find a path from my W to the upper block and from my W to the lower block. But these guys will be distinct because of the way they're constructed, because their parameters, like their entries don't really intersect because of the way that we zero out the entries. So there must be parameters that are distinct from W star, that are connected to W star by this continuous path instead of by a level set of the loss function. So it's basically we get the result because we can are guaranteed the existence of these loss parameters if we satisfy those conditions, and we're also guaranteed to find a connected path between them. So if we have a global minimizer, I guess maybe unless the global minimizer has the block parameters, they're not very clear about that. If it is in that specific form, then there will be block parameters that are different than my minimizer, and that will be path connected to my minimizer. So I'll always have more than just one global minimizer. And those are kind of all the results I have time to show. I think I don't know if, but I want to talk a little bit about the conclusion. So this paper has a few flaws, and I omitted a bunch of proofs, and I omitted a bunch of things where I found a lot of hand-wavy arguments and things that I didn't find convincing. My tentative project is actually to explore this computationally, also because the authors provide essentially no computational examples, and you might say, well, this is kind of hard to provide computational examples. But actually, the loss landscape literature is filled with researchers that do provide empirical results to kind of back up all these grand theoretical assertions. Like, if you look at, oh gosh, the name escaped me right now. Well, if you look at the papers of the neural tangent kernel, the authors of the neural tangent kernel paper, if you look at the authors that did work on the spline theory of neural networks, if you look at the latest Yan-LeCun work of like basically trying to debunk this idea of extrapolation for neural networks, that learning always amounts to extrapolation is what they say, because you always essentially, anyway, some details about the convex hull. All of those guys, they do provide computational results for all their grand theoretical claims. So I would like to see whether this holds to scrutiny, because there are a lot of like bounds here that are given, a lot of results that I think in theory should be computable, and I like to explore it. It seems a little bit daunting because the math is pretty hard. At least, you know, it's easier, I guess, when you explain it. But once you know it and you explain it, it's easier to maybe receive. So if you didn't find it that difficult, that's great. It was definitely more difficult for me than it would have been if I would have had someone explain it to me. But I think, nonetheless, I think this is really ambitious work, and it's really exciting because we should try to arrive at a sort of unified optimization theory for deep learning, or for machine learning more broadly. As we all know, neural networks are sort of black boxes, not just in their representations, but also in their learning dynamics. And I think that, you know, this is kind of a controversial paper again, but I think it's kind of commendable that they're going out there and they're doing this sort of research, because I think it's much needed, personally. Even if it doesn't really matter for like OpenAI and their training of large models and, you know, the bleeding edge and so on. There are other things in the paper that I don't have time to cover, and also hardly during my water. But they also show that you can relax the PL star condition. They also show that tentatively there would be a transition between under-parameterized and over-parameterized systems, and I think that's also an exciting area of research, because like we've been kind of focusing on this dichotomy of like under-parameterized and over-parameterized, but what happens in the middle, right? And what is like that phase transition from under-parameterized to over-parameterized? So I think that's pretty much all I have for today. Thank you for listening. If you have questions.
Yeah. So I guess I'm not an expert on neural networks. How often, in like real world neural networks, how often are they actually over-parameterized to the extent that like these things might hold for them?
It depends on how strict you want to be. If you just use understand over-parameterized as having more parameters than samples, like pretty much all the time.
Okay.
If you want to consider this idea that the number of samples is not just enough, because like, for example, the dimensionality or the shape of the manifold that those data samples form in their own input space will condition how many parameters you actually do need, as will the architecture of the network, then that's a little bit more difficult. And in fact, there's a lot of research in this area of trying to gauge the complexity of neural networks. We have measures of neural network complexity. We have a lot of them. The most simple one is parameter count, which is like how many parameters I have. But again, it's not as easy as saying that I have more parameters than inputs, therefore it's over-parameterized. By that notion it is, in the sense that the model is more complex by parameter count, but there are other notions of complexity. There's one that came out really recently called geometric complexity, for example, that tries to look at the Dirichlet free energy of a network, which would essentially be like the norm of the sum of the norms of the gradients of the particular function on the data set. And there's all these notions that people are coming up with, but none of them are taking hold. Like, so it's kind of hard to say. But like most definitely would be like the number of parameters exceeds the number of samples.
Okay.
Yeah.
Cool.
Yep.
And what is the threshold after which, like, for example, if you have like 5 samples and 7 parameters, like, or if you have like 10 samples and like 1,000 parameters, what is the ratio?
Well, again, there's no simple ratio. Like, it will depend on the distribution of the data, like what implicit manifold they form in input space. It will depend on the architecture of your network, and again, like if you give like 5 and 7, I think that, I mean, all of this is kind of trying to analyze like really, really large numbers. But it will depend on a lot of things, right? Like the dimensionality of the input is one thing. It's not the same to have like, let's say 1,000,000 samples that are one-dimensional, there are 1,000,000 samples that are 100-dimensionals, because you can fit a lot more geometric complexity in a 100-dimensional space than in 1-dimensional space. So all of those are constraining, let's say, or inducing different topologies in the input space and the parameter space that you need to kind of fit it.
So if it's not only the ratio, like how do we summarize, like what is the threshold of something like, you say complexity, right?
We can't, but we're trying to figure that out. Yeah.
So, but how, if we can't figure it out, how we can prove that? If we can't figure that out?
Well, because we know that there's such a thing as over-parameterized networks, and in these analyses, if you look at the actual necessity of this analysis, it really only doesn't need that n is larger than n. That's the only kind of notion of complexity that they have. And that's kind of like what I said, like by that notion of complexity, yeah, most neural networks are over-parameterized. But also there's such a thing as like the degree of over-parameterization or the degree of complexity that can grow past that. And as it grows, you will see more of this behavior. That's actually something that the authors build on, is this work on neural tangent kernels that try to analyze what happens when neural networks become infinitely wide. And this
tangent kernel,
it's the same construction, but because this is not infinitely wide, it doesn't have the same dynamics. So in the infinite width limit, that neural tangent kernel becomes constant or nearly constant, which would also mean that the learning dynamics of a neural network are nearly linear. So there's a lot of exciting work. A lot of that is totally beyond my expertise and mathematical maturity, but there's a lot of exciting work there.
But like, so basically you are saying, so based on their notion of complexity, that like when parameters are larger than samples, like then this network is never locally complex, right?
Mm-hmm. According to this analysis, yeah.
Could you please, like, I mean, if you have time, because
I think it's not locally convex around the minimum.
Yeah, it's around the minimum. However, there are previous results that are, and the conditions for those are slightly different, but they do intersect the larger your network is, that say that there are no spurious local minima, and that's Federer 2020, if you want to look it up.
But still, if you have time, can you go again to the derivation that in the vicinity of local minimum, like if we have even like 5 parameters and 3 samples, by their definition, that is never locally complex?
Well, the trouble is that it depends on these constants that are related to like the smallest eigenvalue of this operator over the entire.
Yeah, I mean, if you wanna do a computational example, go ahead. I mean, come up with a data set and so on. I mean, that's what I'm trying to do, so.
You're trying to do this?
Yeah.
Interestingly, okay, we'll talk about it after.
Yeah, I mean, I'll be showing.
I'm not trying
I'll
to.
be showing you. I'll be showing you as I do it.
I'm not trying to draw your presentations. Just it's very
No,
interesting.
that's fine. I just like I just haven't explored it computationally enough yet. I mean, that's the point. But I mean, I literally text you every day, so I'll probably send you pictures of it as I do it.
So don't mind if I ask you a question?
Yeah.
So there's some results here about arbitrary functions that satisfy this mu PL star condition, and then there's some theorems that relate specifically to multi-layer neural networks.
Yeah.
And so I guess.
Okay.
So which is the one? I guess it's just a matter of getting it straight. The one that says that the minima are all connected somehow.
That one is from a different paper. That result. Yeah.
And that one is for neural networks.
That one is for neural networks. Yes, because it depends on this block construction of parameters that is specifically for neural networks.
Because I imagine that has something to do with the fact that neural networks has a lot of repetitive structure buried in it.
Yeah, right.
So if you swap the rates of two nodes at the same hidden layer, you get the identical output.
Yeah.
And then swap higher layers. So there's obviously a lot of redundancy. And I guess this theorem says that you don't. That's a discrete change, but you can always find a continuous change that would go from one to the other.
So another paper said that all over-parameterized neural networks have local minima connected to each other, right?
No, so this paper says that, I mean, there's a previous paper that says that global minima are connected, and also that there are no spurious local minima, which means that you don't have like these pockets of local minima, like that you don't have this. Because these local minima also would induce local complexity, if you think about it.
For over-parameterized.
Yes.
So the net conclusion from this paper, if a function satisfies this PL star condition, then
yeah, I mean, like the main conclusion, the conclusions are twofold. One of them is that convexity analysis is not the perfect framework, or classical convexity-based analysis is not the perfect framework for deep neural networks that are over-parameterized, which is increasingly what we're working with in terms of machine learning. And also to try to say that, okay, here's this other direction that we can take under this new framework that depends on this PL star condition, and we can show that actually we don't need convexity-based proofs of convergence for SGD, for example. Like, because a lot of convergence proofs for SGD rely on some notion of local convexity.
So this applies to proving if it satisfies this PL star condition, then stochastic gradient descent converges.
Yeah, converges
linearly.
Yep. Yeah, in that solutions
that
exist.
applies only to SGD or to other first order descent methods?
They just talk about SGD. Yeah, I mean, there are a lot of limitations in the sense that most of their analysis, like it's like a grab bag, right? Like some of their analysis is for all models, some of their analysis is just for dense networks. Their analysis does not consider ReLU, it only considers sigmoid. Their analysis, some of their analysis is only for the square loss, but some results are for any loss, so it's kind of a grab bag. It's almost like they're, I mean, I would kind of expect it in the sense that if you're trying to reframe optimization theory for deep neural networks, you're not going to get all the pieces in one paper, certainly the first paper. So, I mean, I like what they're trying to do. I don't know if it's right, and it's definitely a little bit controversial.
I mean, one thing I think is missing, maybe you can correct me if I'm wrong, do they actually prove the existence of a function or a neural network which satisfies this PL star condition?
No, no, they don't. They only say that you need all these bounds and then it follows, but that's the thing, like, I mean, a lot of this is kind of in fact, if you just read the paper and not the appendix, it feels even more hand-wavy. Like when I just read the paper for the first time, I'm like, I mean, I can write a paper like this just being like hand-waving everything. The complicated proofs I showed here are kind of in the appendix, and I guess the structure of the paper is also a little bit confusing because they give like a really long general overview and then they go into all these results that each of them have these controversial titles like "There's no convexity in neural network, section 4," and it's like, it's interesting. I'm very interested in like loss landscapes, representational learning, and learning dynamics. So I enjoyed reading it, but it didn't like convince me. I don't see like the light of our God, Polyak, let's choose whatever.
So it did or did not convert you into the...
No, it didn't convert me. No. But as Aristotle said, the mark of an educated mind is being able to entertain an idea without believing it.